presentation. So the first few words, I'd like to introduce myself. I'm Adam Okniński from the Student Space Association from Warsaw University of Technology. And I'll be talking today about the rocket, Amelia 2 test rocket. I'll start with some history, who we are, who made the rocket. I'll introduce the rocket subsystems, and I'll try to summarize the project. So let's begin with some history. First of all, the Student Space Association works at the Warsaw University of Technology in Poland, and we started from activity at European Space Agency's projects. We have committed into a few programs. Last year, we have also launched the first Polish satellite during the maiden flight of the Vega rocket. But now what I'm going to say are rockets. We have done a small rocket, Amelia. You can see it here in the picture. And now I show something more that we are doing nowadays. First of all, we prepare not only rockets, but equipment. And we are working on a strategy to allow student rockets to lift experiments. And I'm going to show you the Amelia 2 rocket, the idea. So the idea is to build a rocket, a two-stage rocket with both both stages with solid rocket motors, and we want it to be reusable. This is for costs, and we want to lower them as possible, and we would like the project to be something that could be used probably in some more advanced projects. So we want to firstly test if we can separate a rocket, the two stages. And then we would like to probably go into something more into sounding rockets, and perhaps make a contest. Contests as CANSAT contests are worldwide. Both the stages are to be reusable, and we can see the mission profile here. After the launch, the solid rocket motor works for about 2 seconds. After about 1 second, we have the division of the two stages, and we have recovery of both later on by parachute. So, as I said, this rocket already exists. We are going to launch it in 2 weeks in Poland at the military site. As you can see, the rocket is kind of small. It's about 2 meters high, but the interesting thing is it's quite light. It's not only due to using during manufacturing composites and some advanced materials, but it's also the fact that the rocket motors are quite small, what can be seen by the ceiling of the rocket that it can reach. As I can show you, the first stage consists of a small rocket motor. I'll be saying more about it later on, but we can see that the whole first stage is actually empty during this flight, and we are able to put a much larger rocket motor inside. And the second stage consists of a same rocket motor. This is to have some more simplicity in our project, and we want to test such a rocket before we reach high Mach numbers. And firstly, if we want to test the separation of the modules, we want to do it at a fairly low altitude so we can see it and monitor it from ground level. As for payload, we have a GPS tracker, we have a computer, and we have a camera on board. The camera on board is surprisingly in the first stage. This is due to the fact that we didn't want to make holes in the structure of the upper stage, and therefore we have in the payload bay we have just electronics now, but possibly we can take more experiments on board. So how did we actually do this? Firstly, the idea was to develop some skills in Poland at the Warsaw University of Technology. And we decided to use programs such as CATIA. The whole rocket is modeled in it, as well as all the supporting and grounded equipment. Moreover, we have programs that we design solid rocket motors. These are programs that mainly cover the interior ballistics. However, we work also, of course, on finite element methods, for example, in ANSYS, and we try to optimize the rocket elements to use the skills later in more advanced projects. As for the structure, unfortunately, I have not I don't have here the most recent photograph, the most recent state, because actually it was being painted at the moment. So we can see how the rocket looks next to a friend. The structure is mostly composite. The interstage is from duraluminum. We have used honeycomb structure, as well as at the fins we have aluminum alloy leading edge. As for the rocket motors, this is something we're most focused on. The rocket motors are composite structure and reusable. That means we have the same rocket motor. We can use even the same nozzle, the same after end. We just insert new rocket motor grains and the new insulation. The rocket motors are, of course, small, as you can see, but they have quite a good mass fraction for such a small motor. Of course, if we look at rocket motors from Vega, then we could say that they're, let's say, 92% of solid rocket mass propellant. Here we have about 45. But for a rocket motor that is below 1 kilogram, that's a fair result. And we have been comparing these rocket motors with rocket motors used, for example, for separating stages in space during space flight. So we're trying to develop rocket motors that could be the same class. Of course, the propellant is not yet space rated, but we're working on this on the mass budget, and the rocket motor up to now work fine, and they proved that they are reusable. As for the payload, as I said, we have the computer on board, camera and GPS tracker. The electronics are quite simplified. We have an IMU on board, inertial measurement unit, as well as we can measure the pressure and things like this during the atmosphere. It's not a classical sounding rocket, and it's not very impressive in a matter of altitude. But as I said, we want to first test some things and later go on further. The recovery is made by Pyrgon igniter, and we have exposed the parachutes. And this is also just before the separation of stages. It's used to separate the stages. And the fairing of the second stage is also exposed, and the parachute is underneath, so we can recover both of the stages. So going to the end of the presentation, I would like to show some remarks, our ideas. What could we do next? Firstly, we would like to develop a rocket, a sounding rocket, that could be used in Poland for experimentation, since we have our first satellite on the orbit, and we're working on a few next satellites. We would like to test some satellite subsystems. For example, we could check the connections, transfer communication to the satellite from the ground segment. And moreover, we have some interesting ideas connected with working with institutions that are interesting in just atmospheric sounding. So the idea is to build a rocket. This is actually more an artistic sketch than the true rocket. But the idea is to connect the idea of this two-stage test rocket with the CANSAT launcher that we're actually also developing. The CANSAT launcher is up to 10 kilometers altitude is one stage, but we then want to connect these two and reach altitudes up to dozens of kilometers. And this would be fine, for example, for at least organizing contests for high school students, and maybe some industry professionals. So in conclusion, we believe we're developing some solid rocket motor technology that is, of course, not space rated, but for sure, if you take costs into account, we want the costs and the mass budget being improved. And this project is believed to allow us to send experiments, have a cheap, low-altitude sounding capability, and as well as demonstrating, firstly, the possibility to go to the further, more advanced rocket projects in Poland. So thank you very much. And now I finished quite early, but I believe I can answer any questions. Maybe not any, but any questions I'll try to answer.
If we
I'd love to, but for right now, the military, that's what they told us, that we can't take people from abroad, because we wanted to actually, but unfortunately no. But we are thinking of streaming the event live, so maybe we could manage something more interesting out of this. And some people had an idea of making actually a tweet up during the start, so we'll try to broadcast this in some way.
Can you say something about the cost of these launchers?
Yes, of course. The cost of the rocket launchers, particularly this one, it's already combined with the electronics, with everything, but just the rocket, yes, or the equipment. Just the rocket it's a few thousand złotych, so it's like 1,000 euro. But of course, this is just so that's why we're trying to do it at low cost, and counting also the equipment that is like a launch tower. It's more like a launch tower already for the two-stage rocket CanSat launcher that I've mentioned. This connecting with this, the equipment to make propellants and etc. It's below 10,000 euro right now.
Below 10,000 euro for a small, basically for a launch.
Pardon?
So basically 10,000 euro for launching a small.
No, 10,000 euro for the whole equipment, launch pads. There we have 2 launch pads and a few test rockets, plus so this rocket and the CanSat launcher that we want to connect, plus the equipment. That's below 10,000 euro.
What is the altitude that you expect to reach?
With this flight, the first flight, maybe I haven't mentioned it, it's 3 kilometers. I know it's not impressive, but as I said, we put 2 small rocket motors. And the idea why we're putting these 2 small rocket motors is because we want to see the separation of the stages as low as we can. So we can film it, we can then analyze it, maybe change something. But if we put a rocket motor that fits the stage as nominally it should, then we can reach about 6 kilometers. And the most advanced version is up to 10. But as I said, this rocket is more into testing. It's not what we want to actually achieve in final. And the maximum speed in the first flight is about 300 meters per second. And of course, in the next flight is above Mach 1, Mach 1.5, Mach 2.
What is the payload mass you will have on the advance? Because you said it's 6
Yes.
kilometers, so how big payload can you take
Up to 6 kilometers, we can take about half of a kilogram of mass. And this is the idea to build the CanSat, because like the CanSat standard is half of kilogram. So in the rocket we would like to build further on. We also want to lift about half of a kilogram, and that's how it's going to payload be. But perhaps we're thinking of making the payload bay, although for half a kilogram, a bit larger than for CanSat's standard, so we could test also like subsystems for CubeSat technology.
Okay, one last question. Okay, it was the same question.
So thank you very much.
So, okay, we can switch. So if you want to move in another room or stay, you have time to do it now. Laura is going to talk about
volcanoes in the solar system.
All right. Okay, and Wimby, you have the talk about Franco-German engines for European launchers. And here, so space volcanoes. For this session, please, I ask you to use the microphone when you have questions. Talk are recorded. it's more useful. You can use the one at the desk, or I can try to give you the microphone when you have a question. Wait a bit.
Okay, so we're going to get started on this talk. I just wanted to tell you what you're looking at right now is an eruption of the volcano Eyjafjallajökull, which was erupted in 2010. This video is not mine, and most of the videos in this presentation aren't mine either, but the people that made them, I just took them off of YouTube. They're written on the bottom of the slide. So this example is a guy named Chris Weber. So what I'm going to do is I'm going to give you a bit of a tour of the solar system, talking about volcanism on the different planets in the solar system and how the environment into which the volcano erupts affects what it looks like and what sort of, we're kind of at the frontier of discovery right now as far as volcanoes in the solar system, so I'll give you a little taste of what we've discovered recently and what's kind of in the future. I'm a planetary geologist. For several years I was funded by NASA, and now I'm in France, actually funded by CNRS, studying the Martian atmosphere. So one thing I wanted to say at the very beginning was that all of this space data that's taken by NASA and by ESA, they're almost all available freely online for anyone to look at. I wanted to tell you about this website. It's ASU Themis website. You can find all of the Mars images all the way from Viking or probe all the way to the present probes that are currently in orbit around Mars. It's all free. You can look at it however you want. There are utilities to look at it as well. The other great resource is on Google Earth. If you download Google Earth, it's free. There's a little planet tab. You can move between planets. You can go to Mars, go to the moon. I put up here, they have traverses that the Apollo astronauts took on the moon with little images of where they stopped and videos that they took while they were on the moon. It's a fantastic resource. So all of the stuff that I'm going to be talking about that was discovered, it's all actually available, and you could do some discovering on your own. So why do we study explosive volcanoes? Here's another video of Eyjafjallajökull in 2010. Well, one of the big reasons on Earth why we study them is because they're incredibly dangerous. So you can see in the corner picture, I have a picture of a bunch of pumice stones and dead fish. This is from a volcanic eruption in South America in 2011. Killed thousands of fish in the river. You can see also I put up a map of Europe showing the airspace that was closed by the Eyjafjallajökull volcano eruption in 2010. That was a big thing, disrupted all air traffic in Europe. We have a picture of an airplane. That was the Pinatubo eruption of 1993. And I even put a picture of the French Revolution in there because leading up to the French Revolution, there was a huge volcanic eruption in Iceland, which caused really bad summers across all of Europe, horrible harvests for the whole decade leading up to the French Revolution. So some people say this volcano contributed to that sort of unrest. In a scientific sense, why do we study volcanic eruptions? It's because they're one of the few processes that tell us about something that's going on inside the planet, something that's going on in the atmosphere of the planet, and then we can look at all the deposits that are formed on the surface of the planet. And so it's really a unique probe that we can use to see different aspects of how a planet is put together. So I wanted to show you how do they work exactly. Well, usually you have a bunch of magma, so liquid rock inside the Earth. As it rises, the pressure decreases. It's very hot. As bubbles start to form, the physics is actually almost identical to the physics of a fizzing champagne glass, for example. In a champagne glass, you have at the bottom of the glass, there's irregularities in the glass, and they make these on purpose so that all the bubbles will nucleate at these irregularities and come up in a nice way through the glass. In volcanoes, the irregularities are sort of irregularly spaced through the conduit. Bubbles form. Once you take off the pressure at the top of the volcano, you get an explosion. So this is explosion of champagne, very similar to the kind of explosion that you might see at Stromboli. And what you get after that is instead of the champagne foam, for example, goes everywhere, it stays liquid, since it's not normal for rocks at the Earth's surface to be liquid, they harden. So what you see here is a foam. At the top, if you have a really light part of the foam with mostly air and a little bit of rock, you get what's called a pumice, floats on water. And the denser parts of the foam, where you have more rock than air, you get what's called a scoria, and that sinks. And then all the pieces that just completely exploded, that's what you get volcanic ash out of. So here's an image of volcanic ash in Iceland. This is a picture I took in Askja Volcano. And the little shards of ash in the corner you can see under a microscope. And so what do you get? How do you get different kinds of volcanoes depending on where you are? This is Eyjafjallajökull on the Earth, and then you see Tvastar on the Io, a moon of Jupiter. And so that plume is actually 300 kilometers tall. It's shaped like an umbrella. It just basically erupts into the vacuum. So this is what I'm going to kind of talk about. So the volcanoes that erupt actually under the highest pressure are actually located on the Earth, because deep below the sea is where we have some of the highest pressure, maybe like over 90 bars. At the sea level, it's 1 bar, so over 90 bars of pressure, these volcanoes are erupting at the very bottom of the sea. This is the deepest volcano anyone has ever found. They took an image of the volcano erupting. This is 1,200 meters below the sea. And the pressure is so great here that even though the volcano wants to explode really explosively, like you saw in the other images, it can't. It's tied down by all the pressure around it, and it sort of just bubbles and makes smoke and kind of burbles out lava. And so you get, and then this is an image of a volcano that's actually kind of at the interface. It's a shallow volcano. This is in the Pacific. It's erupting, so you see it's erupting below the water, but it's actually so powerful that it erupts up into the water and above the surface, and occasionally makes an island. The island is wiped away by the sea, makes an island again, etc. And this can actually be incredibly dangerous, because what happens is a lot of bubbles will come into the water column. Until the water column is mostly bubbles instead of water, and ships, which are made to be buoyant on an ocean of water, are suddenly not buoyant in an ocean of air, and they tend to sink. So this happens somewhat frequently off the coast of Japan. So the big warning here is if you see pieces of pumice floating in the sea, it's time to get out of there. So even on the Earth, we have different kinds of volcanoes depending on how much gas is in the magma originally. The top image is a really explosive volcano. The bottom image is where you have still some gas that's driving it because it's erupting into the lower pressure, but not nearly so much, so you get this kind of fire fountaining effect. On Venus, that's our second most pressure atmospheric environment. The pressure here is 92 bars. So if you're on the surface of Venus, it's hot enough to melt lead. The pressure is as if you're at the bottom of the sea, so it's not a very nice place to live. And there's several probes that have been sent there in the Soviet era. And they lasted on the surface for maybe a couple of hours, couple of minutes in some cases, and then basically melted. So here, it's really hard to have explosive volcanoes. There's some evidence of explosive volcanoes, maybe, but like you saw at the bottom of the sea, even if it was explosive, you wouldn't get a very big deposit. On Mars, the situation is kind of like what I described on the Earth, where you had a volcano in sort of shallow water, where there is an atmosphere on Mars. It's very light, 6 millibars. So the Earth is 1 bar. This is 6 millibars. And what happens sometimes is the volcano erupts, it can convect like we saw on the Earth, but sometimes it's so powerful and so strong that it actually erupts above the atmosphere and is basically erupting into the vacuum. And so you get a lot of interesting morphologies on Mars. This is something I particularly study. Where does the ash go if it erupts from volcanoes on Mars, etc. Most of the volcanoes on Mars are extinct, but there's some volcanoes where we have lava flows only a couple million years old, which in geological terms is like yesterday. So it could possibly be that there's still active volcanism on Mars. On the moon, we found volcanoes. This is way back in the discoveries of the moon, looking at the moon. You can see them from the Earth. And they're these sort of dark deposits. There's usually a fracture with a big black deposit around it. That's what happens on the moon, because what we have is we have this kind of, the moon is rather dry. We have this kind of fire fountaining, like I showed you, and maybe you'd get this in Iceland or Hawaii, where the magma doesn't have as much gas inside of it. And then when the Apollo astronauts went to the moon, they actually looked on the surface and they saw these patches of orange material. When they picked it up and looked at it underneath a microscope, they found out that these are little tiny beads of what was formerly magma erupting, like the video that I'm showing above. And so the moon usually looks mostly gray all the time. Actually, these beads come in all kinds of colors: orange, black, green, red. And it all depends on what little chemicals are inside these volcanic beads that are erupting. And the very interesting thing about eruptions that take place on the moon is that, unlike on the Earth, where you have this sort of first you have shattering, but then you have transport in the atmosphere, which makes the beads, which are still sort of liquid, into a bunch of weird shapes. On the moon, you don't have any wind. You don't have any drag force, so what you get is perfect spherical beads of lava, which cool as they're flying through the air and then fall to the surface as these perfectly spherical beads. So these are lunar beads. They call them the green beads. And so you can compare those against the sort of shattered lava that you might get if on the Earth. And then even these are hair-like, very long, elongated hair-like lavas that occur when you have lava erupting into a really strong wind on the Earth. So it sort of it elongates it. And they call this Pele's hair, because Pele is the goddess of volcanoes. So she leaves her hair all over the island. So one of the very new things that's been happening recently is the Messenger Spacecraft. This is a NASA mission to Mercury. It was put into orbit around Mercury in 2011, the first spacecraft in orbit around Mercury. And on Mercury, we didn't even know if there were any volcanoes or not. We had sent a probe by Mercury in 1973. We looked at one side of the planet. Maybe there could be some volcanic activity, but it definitely wasn't sure. What happened was, we took a look, and I was involved in this work, and we were actually able to find many volcanoes, maybe like, I think the number is up to 39 volcanoes at the current time. And actually, the day before yesterday, I was looking at more data, and I could find more volcanoes. So this is a period of true discovery, where every day, looking at new images, finding new volcanoes, all the data is online, so you can go and look at it and find some new volcanoes yourself. So these volcanoes are very similar to the ones in the moon. They're erupting into the vacuum, forming little deposits around the side. So moving into the outer solar system, this is an image of the Jupiter's moon Io, and I showed it to you before. This sort of image of this giant plume, 300 kilometers high, was taken by the New Horizons spacecraft as it flew by on its way to Pluto. And you can see all of those. I have that picture where you sort of see a bunch of dots on the dark side of the moon of Io. Those are all hot spots from volcanoes that are currently erupting on Io. Io is the most volcanically active body in the entire solar system. And the reason it's so volcanically active is because it's going around Jupiter, and there's also lots of other large moons going around Jupiter. And as it goes around Jupiter, they pull at it, and they tug at it, and they sort of knead it back and forth, and it heats up the inside, and it starts erupting on the surface. And so Io is totally yellow. This is because it's completely covered in sulfur. One of the other most interesting moons of the outer solar system, as far as volcanism goes, is the moon Enceladus, which is a moon of Saturn. And we've had a lot of new data coming back from Saturn as a result of the Cassini mission, and the Huygens mission that went along with it. Enceladus is an icy moon. It appears to be venting water into space. And so when the probe was flying by, they saw, okay, we're venting water into space. They were able to fly really through this probe and sample it and saying, wow, this is actually pure water. So in this case, it's so far out in the solar system, the temperatures are so cold that what acts like a rock on Earth, for example, on Enceladus, ice would act like a rock. Ice is its own mineral in a sense. And so the volcanism that takes place here we call cryovolcanism, because it's the same kind of volcanism, only the material is water. And I wanted to point out, I have some question marks on some other planets. On Titan, we're not sure if there's volcanism there. We see small grain particles that could be as a result of rivers eroding things, or it could be a result of volcanoes. On Triton, we seem to have what appear to be geysers. So it's not exactly volcanism, but we have some material in the near subsurface, which is very volatile, which kind of explodes. And so that's an interesting thing. And then, we're still heading out to Pluto. So there's a lot of undiscovered things, moons around Neptune and Uranus, et cetera, that haven't even been touched yet. So it's really, volcanism is something that shaped the history of the solar system. It's very widespread, and everywhere we look, we keep finding more. It tells us a lot about the interior of the planet. It tells us a lot about the atmosphere of the planet, both right now and in the past. And it tells us a lot about how the surface was constructed. And with that, I will ask for questions. So thank you.
Thank you, Laura. It was a very interesting talk. So if you have any question, please ask. And it will be great if you can use the microphone. If you can grab one on the desk, it could be great.
Which is the website where you can find all the info or the data?
Yeah, I will. So on the first slide, the best website to go to is actually just if you Google Themis and ASU. ASU is Arizona State University. And what they've done is they've kind of aggregated all of the images from all the missions. They have European missions. That's the best website for Mars. For Mercury, right now, the best website is, the spacecraft is known as Messenger. You can go to the Messenger website, and they have a huge number of great interactive things and images and that kind of stuff. I'm not as familiar with the Cassini mission, but I assume they have their own website too. If you're really into the specific using the data for scientific purposes, there's a website known as the PDS, the Planetary Data System, and that's where all the scientists go to get the information, where you have all the data in sort of a raw format. There's actually a really cool project that I'm involved with. It's called Inside Out. It's a IMAX movie that they're making, and it was just a guy who went into the planetary data system, took all this Cassini data, and he went to other planets later, and he made just a gorgeous fly-through of the whole Saturnian system just by using real data from NASA satellites. And so this is the kind of stuff, it's not just for scientists, for artists, and for whoever wants to use it, the data's for you.
Question?
Yeah.
How do you explain the extreme size of Olympus Mons on Mars? Because it goes up to 26 kilometers, which is twice the size of the biggest volcano on Earth. How can you explain this big size?
Yeah, on Mars, what we have is, on the Earth we have plate tectonics, and so what plate tectonics do is, so if you have a large volcanic plume in the center of the Earth that feeds volcanoes on the surface, the plates of the Earth move slowly across this source. And so you have Mauna Loa, for example, but then all of the Hawaiian Islands, and there's also an underground seamount chain that goes off of the Hawaiian Islands. If you add all of those volcanoes together, you get around the volume of Olympus Mons. So on Mars, we don't have those plates moving. They just stay in the same place forever, and the volcano just keeps building and erupting in the exact same place. And that's why you get such giant volcanoes, where you see them on Mars. Oh, he was asking about this. There's around Olympus Mons, there's a really sharp kilometers high cliff. And that's actually kind of an open question. A lot of people think that there was a failure of the flank of the volcano and there's a big landslide that happened. That's the theory that I've heard is the most current, but it's still open researching area.
Thank you.
Yeah. Yep.
Is there similar volcanic activity to Enceladus on Europa?
On Europa, no, I don't think we've seen any of that. What we see on Europa is a lot of tectonic activity because like Io, it's being sort of moved by other planets. But you would think there should be some volcanism on Europa just because it's obviously hot on the inside. It has some kind of ocean. But we see sort of what look like a little eruptions of this sort of red material that comes up between the cracks, but we don't actually know what that is. That doesn't appear to be volcanic material. So I would say first order, no, we haven't seen that yet.
Hi.
Yeah.
I was wondering if you can discuss the slide about the porous and non-porous rocks again, why that's important.
Oh, yeah. So I just wanted to give an idea of how volcanic rocks are made. Most volcanic rocks, if they don't have a lot of gas inside of them, are really heavy and solid. But then if you have bubbles forming inside the rock, either they escape and they vent out of the rock, or sometimes they're trapped inside the rock. And so in this particular case, you can just see how instead of having a liquid foam that we normally think about, it's a foam made out of liquid rock, and it just freezes whatever way it was when it got cool enough. And so the pumice is the rock that floats on water, and it's just very interesting to see, actually. You can find like a giant rock of pumice like this, and you can pick it up and throw it in the water, and it floats. And so I wanted to show this slide to show sort of the variety of volcanic rocks you can make, and how you can see literally frozen in the rock. And since I'm a geologist, this is what we're looking for. The process by which this rock is made is literally frozen in the rock, and you can come along millions of years later and look at what was happening at the time of the eruption. Yep.
Does Volcano had the link with life apparition?
It's possible. So volcanoes, they provide a source of heat, and that's one of the things we think is necessary for life. And so you have, say, like at the bottom of the ocean, there's what's called the black smokers, which are these sort of huge hydrothermal vents. So they're sort of driven by the heat of volcanism, but they're erupting at the bottom of the sea, and it's actually a huge amount of interesting life forms and very ancient bacteria that live around these kind of things. So if we were to imagine life to exist, for example, on Europa, it's got an icy shell, it's got a big ocean inside. Maybe at the very bottom of that ocean, there's this kind of volcanism taking place that, even though you can't see the sun, you could have a source of energy for these microbes to eat and live. And so yeah, I would say there's a definite sort of link, we think, between the earliest forms of life and volcanoes. But of course, volcanoes can also be very destructive and end that kind of life.
So is it still a question? Because we don't really know if it's an asteroid that kills a dinosaur or if it's a big volcano.
Yeah,
how is it going?
Yeah, that's an interesting debate. I mean, the latest thing I heard about that was, at first they thought, okay, there's actually huge volcanic eruptions that are around the same time as the dinosaurs that took place in India. So just kilometers and kilometers worth of basalt that came out on the surface, volcanic rock. And so the question was, that is a huge environmental perturbation. Could that have killed the dinosaurs? They thought maybe, what if there was an impact and that caused all this volcanism to take place, which is true. But right now, the people on the volcanic side claim that the volcanism began a significant amount of time before the asteroid hit. And so I think the key there is to really nail down that chronology, because obviously volcanic eruptions can't cause meteorite impact strikes, but the reverse could be true. So it could just be that the dinosaurs lived at a very, very unlucky time. Yeah.
You said that sometimes Mars was erupting so high that it would erupt in the vacuum. So have we ever found material, volcano material from Mars on the Earth?
We have not found specifically like ash material erupted from Mars. We do have several meteorites that we believe came from Mars, and they are all different kinds of volcanic rocks, and most of them are actually pretty recent in Martian history. In Martian history, the most recent period is 3 billion years long. So this really long recent period, most of our meteorites come from there. So when we look at the meteorite, we can see that it's incredibly rich in sulfur, which is a volcanic gas. We can see that it's a volcanic rock, and we can see that that sort of trapped inside the rock are actually little bits of the Martian atmosphere, which is how we know that the meteorite probably came from Mars. And so we compare this little bit of gas to the gas that we see in the Martian atmosphere, and we can see that this is a Martian asteroid. So actually a lot of our information about the surface of Mars, since we've never had samples returned from the surface, come from these meteorites. Yep.
Can you perhaps explain how the detection of an imminent eruption is happening, and maybe also if that will be possible on Mars to detect in the same way whether there is any volcanic activity still going on?
So you mean on the Earth? First
Yeah,
question? Yeah, on the Earth, there's a lot of different ways to figure out that a volcano is about to erupt. Most of the volcanoes that are located near cities have lots of instruments that tell us about the seismicity. So if the Earth is trembling, we know something is going on. If the amount of trembling starts to increase, there's danger of an eruption. There's several times where they've evacuated huge areas thinking that the volcano might erupt, and it didn't. Other times where they've evacuated huge areas, like in the case of Pinatubo in the Philippines in 1993, then there was a gigantic eruption. Everyone was glad that they evacuated. On other planets, there's actually, I heard a very interesting talk recently how they have a satellite that studies lightning. And when a volcano erupts, there's a huge outburst of lightning because you just have particles in the air rubbing against each other, and so you have this huge volcanic lightning. And with the lightning satellite, which has a very fast return rate, they could see volcanoes that are erupting near the poles, because near the poles you don't usually have a lot of background lightning. And so they could say, wow, we have just a huge amount of lightning all of a sudden in a pinpoint location. Maybe a volcano is erupting. And that really helps people who are trying to route airplanes and stuff like that, airplanes that want to avoid volcanic plumes. On Mars, we have imagers that image Mars every day. It's mostly for weather, so they watch the clouds go by and et cetera. And so if a volcano was erupting and it was really obvious, we could probably see it. But if a volcano is just erupting a little bit, we have thermal cameras that are taking pictures of the surface. They could probably find that heat source. That would be our first indication. We don't have any seismometers on Mars, but there's actually a mission that's going to plant a seismometer on Mars in the near future, which, if the volcanic eruption was anywhere nearby, could help us figure out that it was going on and where it was. There's seismometers on the moon, so if there was ever, the moon's been dead for a long time, it seems like volcanism is finished there, but if there ever was a volcanic eruption, you could probably see it with the lunar seismometers. Any other questions? Yeah.
What do you think the effect would be of mining the black markers?
On the Earth? Yeah. I don't know. I think it would be a technical challenge just because they're so deep.
Well, there's a company that's going to do it. I'm just wondering what the effect would be.
Yeah, I don't know if there would be. I mean, I think scientists would say, "Oh no, you're disturbing our, life that we're studying at the very beginning of the solar system." But as far as like an ecological point of view, I don't think that they're, vital to the ocean's ecosystem or anything. I'm not an expert on that. So. Yep.
Is there a way to detect volcanic activities on the planet when, for example, exoplanets or something like that, just by looking at images? Or
There could be a way, because what we've been trying to do is look at the planet, and right now we have a general idea of kind of what size it is, maybe what temperature it might be, but we're starting to get to the point where we could try and figure out what the composition of the atmosphere might be, and then it would be, if you had some kind of atmosphere that was wildly out of equilibrium, then you would have to say to yourself, okay, either something's being vented at the surface. Either its life is changing things, like the Earth's atmosphere is quite out of equilibrium because of life, or it's volcanoes that are putting something into the atmosphere. So I definitely think it's possible. Right now, it would be, I think it's more of at the model stage. We make models of atmospheres and we say, okay, this is what we think they're made of. But a lot of missions are being proposed and launched just for the very question of characterizing exoplanets and atmospheres. And I think, you could definitely find that out in the near future.
Okay, one last short question.
Yep.
If you had the chance to travel the distance, what volcano of the solar system would you visit?
Well, my favorite volcano is known as Apollinaris Patera, and it's on the surface of Mars. And it's one of the volcanoes on Mars that's thought to be explosive. It's about 4 kilometers high, and it's totally surrounded by interesting volcanic-like material. It's actually really kind of pretty close to Curiosity landing site. And so I'm interested to find out, Curiosity is actually going to go and sample some of the stuff that we think might be ash coming from that volcano. And so, you know, I've made a hypothesis, I published a hypothesis saying this could be ash. We might actually get to find that out a lot sooner than I thought.
Okay, thank you, Laura. So now we switch presentations. So right now in this room we have a presentation about Gaia. In room B you have a presentation about, so it's called My Way to Columbus. And yeah. So we have 5 minutes to move from one room to another. Can you just show me if it is so it's visible?
No, it's the...
I don't see the key. Okay, I plug like this. It's a very small key. It's a very small key. Maybe I don't push it. Ah, yeah. No, it's okay. No, but we have 5 minutes.
Yeah, okay.
5 minutes to move from one to another.
The PDF one.
The PDF one. This one.
No, yes.
And maybe...
No,
I think it's SpaceUp maybe.
SpaceUp, yeah. The system SpaceUp, yeah, SpaceUp compatibility. No.
Une petite question, est-ce que Arnaud Demet est dans cette salle?
Just a short reminder, if you have not yet said that you wanted to go to the dinner, you have a paperboard in the main hall to write your name on it. Thank you. If you have already given your name, no need to go there.
One, two, three. Okay, here we go with the next presentation. Right, my name is Torgeir Poulsen. As I said earlier, and I'm working for the European Space Technology Research Center, which is basically a subdivision of this place. This is the headquarters of ESA, And STEC is the major technical development center, and we are located in Holland. So I've been working for a long time now on one of the cornerstone missions of ESA. These are missions which we define every few years for a long duration, let's say. And they are supposed to make unique contribution to science. They are using special, expensive, I would say, measurements methods. And they are supposed to also to stimulate development of key technology in space. And I think Gaia is a very good example of that. So moving on, let me see. Well, these are some of the, well, I think these are all the cornerstone missions we have now. And they are basically involved in observing the universe from microwaves, the latest one there being Planck, as you know. You saw it probably a few weeks ago. Planck results finally, let's say, given to the media, all the way up to X-ray, gamma ray area. Now, astronomy, which is what we are in a way dealing with. In the old days, astronomy, another name of astronomy was, in fact, astrometry. Astronomy was about measuring the positions of stars. And way back to Hipparchus, 200 years before Christ, this was the science, although the application earlier than that was maybe a little bit different. Maybe it was maybe not so much about science, but also about finding which star sign you were born in. So anyway, Hipparchus, he already 180 BC, he measured about 1,000 stars with half a arcsecond accuracy. And with that, he found there were signs. He found, for example, that the Earth is precessing, the Earth axis was precessing. Later, let's say in the Middle Ages, there were people who tried to repeat his measurement and improve them, one being Tycho Brahe. And Johannes Kepler, he did science on that by trying to fit his results, his measurement results of Tycho, to his models of the universe, of the way the star were moving. And he found the famous 3 laws of Keplerian motion. So there's always science coming out of astrometry. So measuring the position of the stars, their velocity, is fundamental to astronomy. And you see that with time we have improved the accuracy. What do we see here? 10 orders of magnitudes. And at a certain time there, with the introduction of spaceborne observatory, you see that the accuracy just plummets, 3-4 orders of magnitude. And you can imagine what is the reason for this always increase of improvements to measurements. They range from everything from improvements to instrument making, accuracy of mechanical instruments, introduction of optics in the Middle Ages. Later, clocks, development clocks, accurate clocks was important in order to, which you are using in the let's say the method to measure the position. Introduction of space in itself, the fact that you don't have to look through a noisy atmosphere anymore. There's no, let's say, turbulence or refraction. Detectors, not having to rely on using your own eyes to look at where the star is. First with these image tube detectors we had in the 60s and 70s, and now later also with CCDs. Again, clocks are important for the way you are actually clocking these devices. And of course, materials. Since we are now operating these instruments in space, you need you can take advantage of new, let's say, advanced materials. So, Gaia, what is it all about? Because did I jump one over here? No. Gaia is basically, our purpose is to try to create a 3D model of the galaxy. And the galaxy consists of something like 300 plus minus 100 billion stars. I don't know if anybody of you have been using this free software called Celestia on the net. And using that, you can kind of move around the Milky Way. And you can also actually upload the complete Hipparcos star catalog of 120,000 stars. And what you see then, let's say this is our galaxy. We are about located 1/3 out about, and you would see then, if you zoom out a little bit using this software, you would see that the whole Hipparcos catalog basically is just around Earth. And how are you able to use a catalog like that in order to, let's say, see how the galaxy looks like when you have samples just around you? You need samples from all across the galaxy. How would you know how this room look like if you only have a few samples? You do a few measurements over there. You need to see that wall over there, everybody. Then you can create a model of how the room or the galaxy looks like. And to do that, you need to look at very weak stars, magnitude 20. I mean, on the dark night, you can see stars down to magnitude 5. Magnitude 6, you have twice as many stars. Magnitude 7, 4 times many stars. Magnitude 20, it means that you are seeing about 1 billion stars. And you can see then stars almost across on the other side of the galaxies. A few times today we have seen this picture of the sky, and you see that the sky is covered by dust, basically. So if you had removed this dust on a winter night, you would see a beautiful image of the central of our Milky Way. But in fact, in that dust, there are certain windows. There are certain locations where you can see all the way to the center of the galaxy. And Gaia will be able to make use of that and see basically across to the other side of the galaxy. So we will make a survey of about 1 billion stars. We will do spectroscopy on 150 million stars. We will see, let me see, yeah, I'm coming back to this actually later. The way we measure it is that we are basically measuring each star something like 70 times over 5 years. But more than that, every time we look at a star, we see it about 10 times. So there's a huge amount of data which will help, let's say, improve the science of astrometry. Now, let me see. Right, so astronometry, we are looking at the positions of stars. Why? Again, here you see a nice idealistic view of the Milky Way. Well, it doesn't look like that. Life is more complicated. Maybe not as bad as on the left side, where you see colliding galaxies, some of them head-ons. Earlier today, was somebody here who was mentioning, not to make people afraid, but that the Andromeda galaxy would hit us head-on. It will be about in 3 billion years, actually. So we can wait. But you see here a few cases. But in fact, our galaxy is already in a head-on collision like that. There are at least one large, well, let's say largest body, called the Sagittarius dwarf galaxy, which we have collided with for many 100 million years ago. It has already looped our galaxy. It's mixing with our Milky Way already now. And if you were able to see through all that dust, you would get a image of a completely different type of Milky Way with basically streams sticking out here and there. So we are talking about maybe up to 300 dwarf galaxies being mixed in with the Milky Way. So how do you see the difference between all these stars? Where does that star belong to? Does it belong to the Sagittarius dwarf galaxy? Does it belong to us, the Milky Way? And you can do that by looking at the so-called metallicity. And from that, you can see that that group of stars belongs to, is different from this group of stars, and you can start actually differentiating between. So you need not only astrometry to see the position of that light dot, but you also need to know, you need to also analyze the light, the color, the spectrum. Right. So, comparing to Hipparcos, which was a mission launched in around 1990, which is now basis for the, which is really the map for position, stellar positional data. It measured about 120,000 stars, and these were all pre-selected. That was the method, was part of the measurement method. Pre-selected stars, where are they? Gaia will work on a slightly different principle I come back to. We will measure all stars down to magnitude 20, that's about 1 billion, which means that they will, let me see how to do this. Yeah, you see the numbers there. We will also, coming back to that, Hipparcos measured only stars. We will see quasars, which are basically active galactic nuclei, something like, or very far away outside the galactic, outside the Milky Way. These are used for creating a reference frame. Reference frame away from the galaxy, and also millions of other galaxies. Let me see. So there are basically 3 major measurements. There's a position. The brightest stars we measure with something like 10 to 20 micro arc second accuracy, micro arc second, compared to Hipparcos, which would have been at least 2 orders of magnitude more inaccurate than that. Photometry and radial velocity. Radial velocity is important because it tells you whether the star is moving toward you or away from you, and it's the last element to create a 3D view of the star. And from that, once you have the 3D view of the star, you know first of all the position and the velocity in all the different directions. You can start calculating the energy of the star. From that, you can defer, in principle, you can defer amount of dark energy in the area. And there's a huge number. I'm not an astronomer, so I'm not going to go into the details here, but there's an enormous number of, let's say, astrophysical properties coming out of these very fundamental measurements. And Gaia is basically all about galactic evolution theory. This is what they want to do. They want to create a 3D census of the galaxy, calculating back, see how it was millions of years ago, and how it will be millions of years into the future, and how it's mixing with other, let's say, objects around. So basically, hopefully on the 19th of September, in 3 months' time, we will launch Gaia from French Guiana, the Kourou Space Center in South America. It's launched toward the second Lagrange point using Soyuz frigate, which is so earlier. So we feel quite confident about that, considering Soyuz have had 1,800 successful launches. So it takes about a month and a half to get there. In addition, we need to do orbit maneuvers, calibration, commissioning, testing out the spacecraft on the way there. So about 3 months after launch, we have something called in-orbit commissioning review, which means that the satellite is basically handed over to the scientific community, although it will be all the time operated by ESA from Darmstadt. This is the principle of Gaia. It's basically, you can imagine you are in the second Lagrange point now. It consists of 2 telescopes looking at 2 different directions. It's spinning slowly once every 6 hours. you're picking up stars from that location, and then slowly over after 1.5 hours, you will pick up the same or many of the same stars in the other field of view. And you rotate very accurately, let's say accurately. You keep the motion extremely accurate to scan the sky. I'm coming a little bit back to that. So that's a small picture of the satellite. I have another picture coming later. That's a launcher. These are the different elements, let's say, of the whole operation. We have not 2 ground stations, but we have 3. We got a new one now in Argentina. Data is coming down to ESOC in Darmstadt in Germany. Something like over 11 hours a day, the satellite is dumping 11 megabit per second. And all of that data is basically stored in ESAC, which is the European Space Astronomy Center outside Madrid, where all the science is being done. So these are the complete schedule, taking quite some time, but that's the way it is with these kind of large missions. There's a lot of development, technological development. We have to do part of this in a kind of competitive phase. Phase B there was actually done twice or by 2 different companies, and we selected what we thought was the best option. And then we are now launching this year, and the mission is 5, maybe 6 years. And then a couple of years after the end of mission, we will have the final catalog. This is how it looks like, basically from, let's say, bottom up with solar panels. We have a phased area antenna. On Gaia, it's very important that everything is extremely stable. So mechanisms of any sort, anything moving is not allowed. Not even a little relay the size of a matchbox or less is allowed, because it will create a mechanical click which will disturb the measurements. So anything moving is not allowed. So we can't have any antennas pointing toward Earth, because Earth is, let's say, moving in our reference frame. So we are using these kind of electronic scanning, electronic antennas. We are switching from element to element as the Earth is moving across the sky from us in order to send data back. And then you see there the service module and the payload, which is basically a large telescope, or 2 large telescopes. Everything is in ceramic, silicon carbide, which has basically been made from a powder, pressed together, infused with a kind of glue, and then heated to several hundred degrees, so you get a ceramic, and then you basically grind a mirror from it. Just the polishing of the mirror took something like 2 years. We thought we could do it with the same company, but we had to distribute it with 3 different companies, because we require, let's say, very high accuracy on the flatness of the mirrors. So that was part of the reason it took a little bit longer. And then you have a huge deployable solar shield. This is the big, let's say, pancake you see around there. See another picture later. And in the end, on the top, basically a thermal tent over it. Here it is. You will see a few more pictures later in the next presentation, but that's basically Gaia spacecraft all ready to go in the test chamber or test room in Astrium in Toulouse. It's something like 10.8 meters across when it's fully deployed. The payload bay is something like 3.5 meters, and it's about 2 tons. This is a service module which consists of basically the main structure, the chemical propulsion system, the micro propulsion system. We have 2 types of propulsion system or rocket engines here. One are bipropellant to just keep the position, but also micronewton thrusters, which are basically pressurized air. It's like really the toy type of of rocket. You inflate a balloon and you let it go. This is just well, similar, pressurized air. And this is what we need in order to control this, the spinning of the satellites. Here you see the payload, you see one of the, well, the telescope. You see the backside of the focal plane. The focal plane is huge. It's a gigapixel camera, 100 large CCDs, the size of a credit card, each of them. It's about like this. You can imagine if you, many of you have cameras here, you take it apart and you look at the CCD or the detector in there, and it's the size of your little fingernail. This is this big. And you need that in order to collect the very little light from a magnitude 20 star, even with these kind of mirrors. Here you see it actually. So basically there are 7 chains, completely independent chains of detectors, and the star will slowly move across, being clocked across, or the star is moving, the image is moving across the detector, and at the same time you're clocking it such that the detected photons, the charge is being clocked in the same way across it. And to do that we need the same atomic clock which we are using in the new Galileo GPS system, which basically gives us a timing accuracy of about 50 nanoseconds over the rotation period of 6 hours. So, yeah, no? Yeah. CCDs, mirrors, yeah. Okay. This is again from French Guiana, where we're going to launch in a few weeks' time. Data, if you had to dump all the data down, it would mean 73,000 terabytes over 5.5 years. Definitely not possible. So basically what we are doing is that we are picking out the star. We detect them at the beginning of this CCD picture you saw earlier, and we pick them out later. Just take the data, the few pixels around each star, and we download them, do some onboard compression. Let me see. So in the scientific community, there's a huge number of students, PhD students, scientists working on this. It's an enormous apparatus in action right now. And I think in the industrial teams, there must have been, I would guess, maybe a couple of thousand people who have been working on Gaia over the last 10 years. So, and in 2021, I think, you will have the final product freely available. And by the way, the data is for everybody to download if you need it. Thank you. That's all. Any questions?
I have time for 1 or 2 questions, maybe.
Yes. You were explaining that you measure the velocity of the light.
No. You measure the velocity of the star in angle, let's say, the angular transverse speed of the velocity of the stars. Well, speed is in this direction. Velocity is when you're talking about the vector, so the 3D components of speed. And the third vector you get with the radial velocity. So.
I also had a question. Well, earlier I saw a movie about the stars that turn around the central black hole, and they were very speedy. Yeah, how will you cope with that?
We'll be careful. First of all, I'm not an astronomer, so I shouldn't answer this kind of question. But maybe these measurements you've been talking about are the stars moving around the central supermassive black hole we know we have in the center of the Milky Way, and even though we might see them in the so-called Bode window, Well, remember that we only observe them. I mean, they have no influence on the operation of the spacecraft or anything. We just observe them. So, yeah, if they are bright enough, we will see them. And but what's interesting is that in terms of observation, and this kind of, I mean, one thing is stars moving around the black hole. Remember that there are also planets moving around the stars. And this is the way we are actually detecting exoplanets now. Basically, you look at a star moving along, there's a big planet moving around it. You don't see the planet, but you see the stars. What is the star doing? And the star is wobbling. And if you can measure this kind of wobble, and to do that you need a very accurate measurement of the position of that star, you can infer that, hey, there must be a planet there. And because of the accuracy, we are measuring the position of the stars. Gaia will be able to measure, to detect all Jupiter-sized planets from here and 500, I think 500 light years out around Earth. All Jupiter-sized planets will be detected through, basically through this wobbling. This is how accurate it is. And we will see thousands and thousands of near-Earth asteroids. There's a huge number of kind of byproducts coming from in addition to just seeing the stars. We will completely map the whole solar system in terms of asteroids. Also something to think about when we're talking about planetary protection.
Okay, thank you very much. Time is over, sorry for the other question. So now we switch presentations. So in this room we are going to continue to speak about Gaia, basically from design to launch. In room B we have the topic about space generation voluntary opportunities, and in the Buzz office warp drive concepts. Okay.
Non, en fait, c'est les prises qui sont un peu dures. Ouais. Tout à l'heure, j'ai eu le même souci, mais il faut pousser un peu. Pourquoi?
Non, j'ai pas l'habitude.
Ah oui, mais une fois qu'on est dedans, c'est pas. Alors, c'est où? SpaceUp.
Non. Vous voyez ça, c'est pas là-dedans? Non, il n'a pas dû la retrouver. Ouais.
Ah oui. Attends, on va enlever celle-là en fait. Ça sert à rien. Là. Continue, vous êtes scanning.
Je m'appelle Ariane, ici Ariane, je t'appelle Ariane, c'est pas
Allez, ouais, c'est ça?
Je prends mon PC, ça m'est envoyé, ça m'a pas.
Je sais pas si la clé qui est pas bien.
Queen Ariane.
Bah oui, si vous avez votre PC.
Queen Gaia.
C'est bon. C'est dans SpaceUp?
Non, présentation.
Celle-là? Et voilà. Ça, on est vu. Désolé. Et en fait, j'ai utilisé cette catégorie. Je vais utiliser les flèches ici, comme ça pour passer. Il faut commencer allez-y en fait.
Hello?
Vous voulez, quand vous sentez.
Everybody. Hello everybody, I'm Isabelle, I'm working on Gaia spacecraft itself. Hello?
Yeah.
So please be indulgent with me because I'm not fluent in English. I'm not used to do a presentation in front of a lot of people. So, so as described before by Torger, what about the Gaia, the design on my presentation is about the design and after that how to construct the spacecraft. So in fact to observe, to do a mapping, a 3D mapping of our Milky Way, we have to make some observables to describe objects. So we have to know the color of the stars, so it's a chromatography. We have to measure an accurate distance of the stars. So we are expected to measure above 10 microarc-seconds. So like a piece of 2 centimes or 2 cents of euros on the moon from the Earth. So it's the astronomy part of the Gaia. And after that, to do a 3D dynamics mapping, we need to do a measurement of the radial distance and the radial velocity. So we have a Doppler measurement inside the spacecraft. So it's the spectrometry. So Gaia, the main objective is to observe stars, a billion of stars, so until magnitude 20. And to do that, we have 3 instruments on board the spacecraft, so to measure position, distance, proper motion, and physical properties. So as explained by Torger, so I go quick, the spacecraft will be spin around itself during the orbit, during the mission, to have a complete sky observation of the sky, of the Milky Way. So at the end of the Gaia life, each object should have been seen 80 times. How to have an accuracy and stability of the spacecraft? The spacecraft will be orbit at the Lagrangian point L2, because it's a suitable stability point of near the Earth and between the Sun. So it will be at 1.5 million kilometers far away from the Earth. So how to concept from the concept to the launch of the spacecraft, it should be 16 years. And after you have 5 years of in orbit for the mission. So 3 instruments on the spacecraft. So a photomet, a spectromet, and an astromet. They are sharing all the same focal plane. The focal plane, so it's 106 ccd. So about 1 gigapixel, a big photographer. Ah, j'ai quelques soucis. I will see after that, okay. So to have an image, we have to have a telescope, so we have combined 2 telescopes on the same focal plane. And to avoid any perturbation of the image through the telescope, it has been done, the telescope is mounted on a torus in carbon silicon carbide, to have a passive thermal design and to have stability in temperature. Passive thermal design, temperature design, and strain. Sorry. So the payload in assembly, it was done in Toulouse, at Astrium Toulouse. So you see the carbon silicon structure in torus and the mounting of one of the first primary telescope mirror. So each, we have two primary mirrors. They are each on carbon silicide on about 1.48 meter long. Quite a big mirror. To measure the radial velocity measurement, we have this instrument made of lenses and the nanostructure network. The overall spacecraft, so in orbit it should be like that. So how to assemble the spacecraft? You have to put each subassembly together. So it was done in Astrium Toulouse since July 2010, since 3 years. So you have a carbon structure itself. After that, you put a chemical system on a chemical propulsion system or micropropulsion system. You put the electrical harness to connect all equipment. After that, we put also equipment, electronic equipment. Then you put the payload, the instrument itself. You put also the thermal tone structure on the payload that cover it onto, I will explain, and the deployable sun-shield assembly. So in July 2010, the service module is arrived in Toulouse. Donc a carbon fiber structure made by Quasars in Spain. The propulsion elements have been made by Astrium UK and TAS Italy. And the electrical harness Quasars by Quasars, and everything was previously tested, assembly and tested in Stevenage in UK. So we are in complete ESA European spacecraft assembly and test. In October 2011, in October 2010, it's one of the first steps of the integration in Toulouse. It's the first switch on of the service module with the power, with the calculators and the interface, and the first central software, flight central software. In October 2011, we have the sun shield was delivered to Astrium by Sener in Spain. Here you can, we have integrated the sun shield on the spacecraft, and we did a deployment on ground. We use zero-G elements to simulate the space absence of gravity. So in order to make this deployment, it takes around 1 month of preparation. So I'll let you see what will happen, in fact, in the orbit, nearly 1 hour after the launch. It's an accelerate video. So the sun shield is about 10 meters diameter. It avoids that the spacecraft and the instruments payload itself will be it avoids that the payload will be disturbed by the sun itself, and for the temperature, to maintain a temperature inside the telescope itself at minus 130 degrees. The service module itself will be running at 25 degrees. So the thermal aspects on Gaia are very interesting and very tested, because we want to conserve, to keep the thermal stability at each step of the orbit and each step of the mission, to have the accuracy, the goal of the accuracy. Du coup, j'ai raté un truc. Ça va? Ouais, merci. Sorry. So in autumn 2011, we have performed the mechanical test of the spacecraft. So we put all the spacecraft on checker, in acoustic chamber, to simulate the spacecraft during the launch. In fact, we want to verify that the spacecraft will be okay after the launch, because also we verify if the structure, the different fixation, could resist to the launch. Even we have not have been delivered with all the equipments. We have made, installed dummy loads, and to simulate the propellant that is resin, for example, but very hazardous materials on ground. We have filled the tanks by nitrogen or isopropylic alcohol, but we stimulate the weight on the mass of the spacecraft overall. After vibration test, we have performed also a new DSA sun shield deployment to verify that everything is okay after the launch, and we can have a successful deployment in orbit. J'ai juste un problème. J'ai un problème. Attends, j'ai juste un problème, c'est que les vidéos se lancent pas. Je les lance après, à côté.
Si elles sont sur l'écran.
Ouais.
Ok, ben on s'en
Mince. Sorry. Du coup, j'ai... So in parallel, the mechanical test of the payload has been made also. Here it's an example of vibration that you could that occurred on the vibration test that occurred on the payload. We have no sound, but you can see that the payload is moving, is very moving, and the 10 Gs are seen by the payload. It's not an accelerated video this time. Je sais pas dire. In April, so after that, in April 2012, we had the delivery of the phase array antenna. So this antenna is a specific one for Gaia. It's not as usual. It's an omnidirectional antenna that could. It's allowed to the spacecraft and the memory, the data stored in the memory to be sent to the Earth during the mission. And the antenna, due to the specific orbit of the spacecraft with the spin, we need this typical antenna with an overall multi-directional. It was also an important step for us, for the team. In summer 2012, we have performed the thermal vacuum of the service module. Here the pictures of the spacecraft into the chamber. It's also in Toulouse at Intispace Space Center. So we put the module into the chamber, we do the vacuum, and we in fact simulate the temperature viewed by the spacecraft into the space. So we verified that all the equipment are well running and onto vacuum, and that the thermal predictions are confirmed. In December 2012, the payload thermal vacuum also occurred. It was done in the Centre Spatial de Liège in Belgium. But the goal is not exactly the same. There we simulate also the space environment, but to verify the performance of the three instruments in the low temperature, and if we can have good images and the stability as wanted. So last February, we have the payload delivery. So now we have a complete satellite since this date. So due to avoid any contamination, for example, you can see people are wearing mask and total combinaison, okay, wearing gloves. So we don't want now to pollute the spacecraft on the mirror. It's like with your glasses, if you put your fingers on the glasses, you don't look very well after that. If you have some dust, it's the same. So we don't want that pollution on the mirrors, on the CCD also. After that, we have put also the thermal tents. So the thermal tents is a cover to protect the instrument from outside and to keep the minus 130 degrees inside the cavity, and to keep the stability for the goal of the mission. In March, we are beginning the final verification. So for each satellite, we have to measure the weight, the center of gravity, and the inertia moment for the launcher, in fact, to assure a good positioning into orbit by the launcher. It's data. There are data requested by Enceladus in this case. J'ai presque fini. And after that, we have also performed EMC test in an acrylic chamber. We have a specific setup. You can see people in front of the setup, so good size. We perform this test to verify that all equipment are functionally without disturbing the other equipment, and in particular the phase array antenna, because this antenna, when working, it won't disturb the other equipment, and especially the mass memory, for example. So now we are finishing quite the assembly of the spacecraft and the testing. We are doing all the things to final the assembly end of June, and the launch is expected for autumn, this autumn, in Soyuz. On Soyuz, from Kourou in French Guiana. The spacecraft will be transported to French Guiana in two separate in two separate parts. In fact, we couldn't assemble the sun shield in Toulouse and put into a container. It's too big size. So we will assemble the sun shield once again in Kourou and test it and do a deployment there. So the launch campaign will take around 12 weeks. So K number, the mass of the spacecraft at the launch is about 2,000 tons, 2 tons. The mass propellant is 300 kilo, so the propellant itself will be fuel into the spacecraft in Kourou. So the diameter of the sun shield is about 10 meters. You have about 1 gigapixel of CCD and mass memory of 1 terabit. So at the end of the life of the mission of Gaia, we found we think that 1 teraoctet of data will be done. So about 10 years almost for astronomer to do some switchers. If you have any question, quick.
Perhaps
if I could answer.
I have one question. Did you perform any shock tests on the silicon carbide structure? Did you perform any shock tests on the silicon carbide? On your development process, you show us a random vibration test. You show us a video on the random vibration test. And did you perform any shock test like alpha sinus or hammer shock test on the structure?
Perhaps during the development of the structure itself, but not at the spacecraft level. The only shock test we performed is with the adapter of the launcher. Okay. We are simulating the shock at the separation into orbit. So we put the spacecraft with a lifting device, and we do the separation of the clamp band that link the spacecraft to the launcher adapter, and it's the only shock test performed at spacecraft level.
You talked about simulating zero-G for deploying the panel. How did you manage to?
In fact, we put counterweight.
The
yes,
cable and
cable and counterweight. Okay. It's quite easy, but not in principle, but not easy to do, to install and so that, and to equilibration for the equilibration and so that. Okay.
Just one more question about the cleanliness contamination. What is the level you work, the clean room levels you work on for the CCD or structure integrations?
When the payload is not protected by the tent cover, as a thermal tent, we are in class 100, if you know the term, and for the spacecraft overall testing, we are in class 1000. Yes, ISO 6.
Okay, great. We will switch to the next presentation. So here in this room, it will be about Mars 1. Is it a realistic project or not? In room B, it will be about Neo Shield, preparing to protect Paris. And in the Buzz office, we'll speak about space technology for disaster management.
T'as vu ça? C'est relou. Il faut l'éteindre à chaque fois.
On le savait, mais bon, là, on peut rien faire. Ouais, mais c'est... Franchement, quand il y en a plusieurs qui parlent, c'est chiant.
Unless you have pretty good eyes, this is an interactive session, so I would suggest you to move a bit forward the end of the room to see the board.
Can I echo that sentiment? I really want your input, so the further you come closer, the better you can read it, and the better you can engage. We can engage each other, because that's what this is all about. It's a brainstorm session, and we want to do this together, and I want your input. So, please. Okay, so hello everyone. I'll start with a bit of a disclaimer. I'm not doing a presentation on Mars One. I will give an introduction, but I'm not an expert on Mars One. I just think it is an utterly awesome idea, and I think down here we have a lot of intelligent people with the right kind of skill set. So my idea was to bring forth the power of us. Since I want your input, I would like you, I'm not sure if the system can handle that, but can they all turn on the microphone? Does that work? Damn it. Okay. I was kind of hoping it would. Okay, well, in that case, yeah.
You need to press and then...
Yeah, okay, so you have to press and press again when you're done talking. Okay, is there anyone who does not know Mars One? Good, that they did, oh, you don't know Mars One, or? Okay, Mars One is an initiative to land people on Mars in 2023. It is a private initiative, and there is no government money involved. They're just going to make it so awesome that the people will want to pay for it. And the way they're going to do this is by making it a reality show. People fall in love with everyone that is being sent to Mars, and that's why they can sell the rights for the media, and thus way they can fund their mission to Mars.
Is it serious?
Sorry? Yes.
Serious?
Very good question. It is serious. That is the point. It is a small Dutch company, and what they're saying is the Olympics have gathered, I think, up to $1 billion in profits for just one year. That was last year, London Olympics, and this is landing on Mars, colonizing another planet. So this is the biggest event of the upcoming century, of the last 2 centuries. It is so gigantic. It is the next step in human evolution, and I am extremely excited about this. I think you can tell that I'm excited about this. And Mars One, the company believes that they can get the whole planet excited about this. And I believe it should be possible, but what we have seen over the last year is that excitement has been lackluster, to say the least. They did a conference like a month ago, and they had a room booked for 300 people, and there were maybe 15 journalists available. The live stream was viewed by 1,500 people. And I've been wondering, why is this response so lackluster when we're talking about such a huge, gigantic event? Yeah, go ahead.
Hello. I'm excited that there are people having big ideas, and I think we should put ourselves out there. So don't get me wrong, I'm not a party pooper, but I have so many issues with Mars One. Mm-hmm. Just so many things. Have they thought about the ethics of it? They don't have anybody who does ethics on their team. Have they thought about radiation shielding? Have they thought about how you're going to feed people on Mars? They keep saying they're going to sell the rights of this and earn lots of money, and everyone's going to watch it. They reckon it's going to go for 10 years. Now, okay, Big Brother, that ran for 10 years, and people still watched it. But every single day, they gave them a new task, and you watched them, and you had the annoying people, and you watched the arguments. When I asked the guy, you know, are you going to show the arguments, or if something goes wrong, or if somebody gets hurt? They said, no, of course not, because, you know, that would be unethical. Okay, so who's going to watch a really boring, I don't mean it, but like, you're traveling 6 months, and you have 4 people in one spaceship, and what are they going to do every day that's going to keep the public interested?
Exactly. Very good question.
Also, like, it's a one-way trip. Surely, if you're going to if you want to be traveling with people, you want them to want to stay alive so that they learn everything properly and they don't kill you. You know, you don't want them to have a death wish, do you? If you're traveling with them, so maybe the only people, maybe it's catch-22. You're only going to go if you're a little bit crazy, in which case, maybe you shouldn't go. Also, they're going to train you for like 10 years, and these people, they might think, okay, well, I want to go to space. Look, I want to go to space as much as the next person, if not more. But in 10 years' time, you know, I might apply now, but what if I suddenly have a family, I have other things? In 10 years, I might drop out of the program. Do I really want to be traveling with people that, as a reality TV show, who do you keep in? The really annoying one, because it's funny to watch everybody argue with them. Do you want to be stuck in a spaceship and on Mars with the one person that the public voted in because it was funny, because they had an annoying voice? No. So that's me playing devil's advocate. I don't think it's going to work. Sorry.
Okay, thank you. Yeah, go ahead.
Yeah, on my side, I'm kind of worried about the credentials of the team that's proposing this initiative. Like, these people, what are their like technological or even project management credentials? Because if you look at the Apollo program, we talk about 200,000 Americans working on this in the 60s, and they had the equivalent of $100 billion spent over maybe 8 or 9 years. And it was like the president who said, we go to the moon. This is just a bunch of funny guys who said, let's go to Mars.
Yeah, and what they say...
My major worry is it sounds more like a marketing initiative than a real project that's really going to take place. It's very exciting. I would be the first one to fly there, but I'm really worried that it's just like, you know, a nice dream.
I agree, it is a nice dream. And what I think their point is, and what I think a main point is there, is the marketing. With marketing, you can get that kind of money that you that could fund the technology, and they don't have the credentials to build that technology. But what I believe is that the industry can build the technology, and you don't. If you have the marketing to gather the money, then I think you can have the industry.
But then we
build the
need
technology.
somebody like to manage the whole thing. Who's going to do it? Because like once again on the Apollo program or the ESA program, we have the ESA, we have the NASA knowledge and people and project managers. Who's going to do it? Because Mars One doesn't have any kind of project managers doing this with a space background.
Yeah, if you turn off yours.
Actually, can I just react on that? I actually happen to know the guy which is behind the idea of that. And I can tell you, he's a very, very good systems engineer, and he's very good technically. Also, as a side note, we were talking about Big Brother. The people that are behind that, supporting that, and don't take me wrong, I think it's a stupid idea. But the people behind that are the people that invented Big Brother. In the Netherlands, they're huge in reality TV. They are big, really. They invented that. So the people behind the funding part, I think they have a very, very strong legitimacy. And technically, their legitimacy is quite good. They actually think that they want to reuse technologies already proven. I mean, Dragon. They were talking about using Dragon. Remember, Musk announced last year or so that they want also to land on Mars. They're developing equipment for that, and they have those very nice CGI things. So, I would be, a bit cautious when, when saying that those guys don't have legitimacy in their field or the technical capabilities, because they have it.
Yeah, go ahead.
I was just thinking, because where I work, we often are looking at Mars One with comparison to this new plan that I can't remember what company came up with. To send,
Inspiration Mars?
Yeah, the 2 people in a loop around Mars. And so we were just saying, I think that Mars One would gain legitimacy if they put forth a plan, kind of like the plan that these other people put forth, which is to say, this is all the technology that we already have, that's already in development or already done, that we're going to use. And then we're going to work with the space program in order to make that technology happen. Because even if you had all the money, there's just huge technology leap between going to Mars and sort of flying around it and coming back and actually setting something down on the surface. And so I think it would add to the legitimacy of the project if they did partner with people who had already done that, and also if they showed a very specific plan showing what technology that they intended to use to get that done. I think that's the big gap where people are saying, I don't think you're serious about this because we're not seeing your plan. So we're not coming to your events because we think it's a dream. But if there was a real plan put down, I think people would be more likely to get behind it.
Yeah, go ahead.
And I'm pretty happy that you say the Inspiration Mars, because I really believe that this is exactly the technology, they need in a sense. And by Inspiration Mars saying, we're going to do this flyby, they're generally giving them, this is all the technology you need to go there. Because, the flyby mission is you start from Earth, you fly to Mars, you fly around, and you return on Earth. What about just using the same lander you have for Earth atmosphere to just go on Mars? So the technology is, from this perspective, for me, the technology is there if Inspiration Mars managed to do the flyby. The question is, or the supplies and all the cargo which is needed. But the most important stuff, or the most complicated stuff, I would say, is to get the humans there, get them there safely. And that's what the Inspiration Mars is generally going to do. So I don't think so that it's a question if the technology is there. The technology is here, we have it. It's more about like taking a different approach how to handle this technology, and really don't do everything completely perfect, but use what we have, and maybe don't have the most comfortable spacecraft which is brilliant to fly and all the stuff, but just take what we have and do it.
I agree completely. Does everybody know what Inspiration Mars is? Well, it's a flyby mission to Mars for 2018. So they're aiming at flying around Mars with a free return trajectory, so they will not have to do any propulsive maneuvers after they've left the Earth, and then do a manned flyby of Mars in 2018. And I think you're completely right in saying that that is most of the technology you'll need, and especially if that is successful, I think that is also what will show, if they can partner up with them, that would validate their plans to land on Mars in Mars One. So I think that can be a really good idea if Mars One might somehow partner up with Inspiration Mars and like saying the funds we generate now we're gonna put to Inspiration Mars and use that as a validating mission. I think a big problem for Mars One is that they don't just want to do the flight, they want to build a colony including the infrastructure. So they're planning to send the first communication satellite in 2016. And since no one can come back, they have to keep supplying them. So there is a lot more to their plan than just Inspiration Mars. But yeah, I haven't figured that out yet. Go ahead.
Would there be some professional crew with them?
Well,
no, but because there need some people that know how to fly in space, minimum, no?
Yeah, what they want to do is, yeah, they want to train the people they select to be professional. That's the idea.
Guardian keeper or this kind of stuff? No.
No, but the trainers will be probably. So yeah. So it is a very good question. They will, perhaps you'll have to have someone experienced to go along. It's one of the things I'm going to write down. Go ahead.
I'm sorry, I still don't buy it. I don't care if they have the Endemol people who are absolutely fantastic at making television. I used to work at the BBC, and there are so many conversations that you have about, what do you put on the news showing people when they're dying. There was a documentary that was made with a guy with a terminal illness, and they wanted to show the moment when he died, and there was a huge ethical question around whether you can show that. I can't see broadcasters with the cash signing up for something like this, because, you put your brand to something and it blows up on the way, or you just leave these people and they're, they get radiation sickness and they're dying. That's, firstly, ethically, not sound, and in a marketing way for the broadcaster, not good either. So where are they going to get the money? I don't think it's going to be from broadcasting.
I think we also have to consider that, what you're talking about is traditional broadcaster like BBC, but you have way many more ways nowadays how to broadcast stuff and how to get the back revenue out of that. And just the YouTube is a perfect example of how to generate revenue from putting something live and giving it available to other people. So.
Yeah, but that's not the example they're giving. They're giving the...
I know, but that's they might have one way of doing it, but if this is a showstopper, there are other ways. So it's...
But that wouldn't work, because in order for something to make money on YouTube, you have to have it on YouTube, and the people have to watch it, and you have the adverts, whatever. That means that they have to have spent all the money to get everybody there before they have the content. But they need money to buy, they say they're going to work with SpaceX, but they need money to do that. And if they are going to work with SpaceX, you really think that Elon is not going to be the first person on Mars with his own technology?
No, what I meant was that the very important part of the concept is the training, is the part here on the ground. So, I really believe that their plan is to make a lot of revenues just here before everyone really flies. So all this selection process where people are signing in and where they are going to train for being a new colonist on Mars and all the stuff. I think that's maybe something which is completely ethical to do, because you have a people training years to go for Mars, and there is no radiation sickness there. There might be a lot of conflict, and you have a Big Brother-like style of stuff, and the aftermath might be way more
yeah, and
justifiable.
You could localize that and send it to 100 different versions, and if that all is popular, then you could potentially get money.
So you're saying do this thing but not send them to space, but the whole idea is sending them to space. Unless you want to remake the thing which they did in England, where they chose, I think, maybe 15 people and trained them to go to space, and then they put them in a shuttle shuttle, and they sent them off to space. And they said, "Don't worry, we have a special machine that keeps gravity on, so you won't, you won't feel anything." And these people, they opened up the windows, which were all blocked in their launch, and then they saw Earth. And then the host just walks in the back of the spacecraft and is like, "Sorry guys, you didn't go anywhere."
Well,
you could do that, but it's not the same as like exploring Mars.
No, but I think the idea is to make your money on Earth with the whole selection process, and then out of that, fund the best of the best of the best to space. And I think it is achievable. And sorry, you had something to add?
Yeah, I do think they already started the selection process, and you can apply for that one. And
Yeah.
it's not free; you have to pay.
Yeah, exactly. They have.
So, that's also a way that maybe they hope to get money for.
Yeah, they make some money that way at least. But I think this can barely keep the company running.
Did you personally apply?
Yes.
And how much money did you pay for your application?
I had to pay $34.
How much?
34. It's a scale between 0 and 71, depending on how wealthy the country is you live in. In China, it's $11.
I think a big question is just, if the technology is there for people to actually survive on Mars for any length of time, or if you're really just going to have a show where people fall in love with these characters, these people over 10 years, and then watch them die. Is that really something you want to make a TV show about?
Yeah, personally, if that would be the show, I wouldn't have applied. I believe it is about building a self-sustaining colony on Mars, and I think there will be no. Well, science is not the primary mission. The primary mission is colonization. So I think that is, someone last week suggested it somewhere, that it would also be a lot more credible if they presented a plan like it'll take this long for the colony to be self-sustainable, because then you truly have something that will be built up, and then you can show that you're aiming at this next step, this multiplanetary species. Yeah.
According to that point, if they do succeed to build something like a colony on Mars, I'm not a lawyer or something like that. What's the legislation about that?
Yeah, there is none. And that is also the question of on ethics. Not only will the marketers agree, but will the countries allow their subjects to leave and die in space? It is a big question.
The company is from Netherlands, so the colony will be Netherlands?
Well, I think the colony will be Martian, but...
There are some rules for the space. There is no ownership of space. So even if it's Netherlands, it should not, in theory, become from Netherlands. But that's theory.
Yeah, exactly. There are the international agreements that do govern it slightly, but they never even consider these kind of questions. Okay. Okay. Yeah, go ahead.
The question is, how are you gonna enforce this on Mars? You have a group of people who are living there. They are some kind of dependent on Earth, but how are you gonna force them to do some legal organization which is related to Earth, because you are not there and you cannot get there? In a sense.
Yeah, I think the colony should be self-legalized as soon as it is a major colony. But yeah, this is all depending on whether we can do it. And what I wanted to achieve today was list a couple of problems and see what we can do as people to address those problems, reduce the severity of those problems. And I think the ethical questions are a major problem. I think we've heard from many people around here that the technology might not be as big a problem as some people think, but and on the other, Elon Musk is working on that. Go ahead.
So I just have one question as a big thing that I think we need to think about, is if we're going to send these people up there and have a colony, it needs to be self-sustaining. It needs to be a closed-loop system. Like, we've had the space station up there for, we've had people living up there for over a decade, and that's not even a closed-loop system. So what do we need to do, and how can we create a system that would work so that we don't have to keep supplying them? Because if we pop them up there and then, the company goes bust, who's going to be sending them food?
Yeah, I think that is a big question that has to be addressed. How can the colony get to a self-sustaining situation? And I think that might be the biggest question besides the ethical question. So to wrap it up, I think I have 2 minutes left. I'm making lots of noise here. More. I would like.
Actually, just you have 7 minutes left because there is a break at 3:30. So.
Okay. Well, I think I'm still gonna wrap it up. I've heard lots of really interesting points, and to wrap it up, I'd like everyone to take a minute. Well, take an hour. Take time to think about these problems, these ethical and the self-sustaining system. And please, if you think of good arguments pro or con, or if you think of new ideas that might lead to technologies, do something about it. Because I know, and I realize there's lots of problems, but I believe that as mankind, we can solve these problems. And if we can motivate enough people to think about this the right way, then I think we can do this. And I think that would be utterly awesome. So if you have an idea, connect with me. I'm on Twitter. I'm an angry guy, angry_B8. That's me. Talk to me, give me your ideas, and I hope I will be becoming lots more active there. And let's aggregate them and see how we can get this done. That's it. Thank you all. It was really cool.
Okay, thank you for this interesting debate. Actually, we are not having a break right now. We are a guest here, Leopold Erhardt. Yeah, but we do some tests first, and then we will have an interesting talk.
That went better than expected. That went better than expected.
Well, I have to say that I just like people like you because
Hello. Everyone, please take a seat. Everyone, please take a seat, even at the back of the room. We're going to continue. We'll have a pause right after this session.
Je parle là? Ah non, je parle ici. Ok. Ouais. Ok. Ça, j'utiliserai après l'autre. Hein. Je me présente directement. Ou vous faites,
Oui, c'est vrai que. So, we have welcomed a new guest to the room. Maybe you have noticed him. So, Leopold Deyarts, who's a NASA astronaut, and so who is the next guest speaker.
All right. Good afternoon, everyone. Very happy to be here for this SpaceUp event. And just like to say that you know that space is not only up, right? It's all around us, and it's maybe a little bit more obvious when we are in space. Not too much in the space station because it's very close to Earth, but for the astronauts who really went very far from the Earth, like the moon missions, it was even more obvious that space is all around us. I had a chance 5 years ago to fly in space in the International Space Station. It was at this time the station was still in construction, and it was the beginning of a new phase in the assembly of the ISS, with the start of the assembly of the non-Russian or non-American modules. So Columbus was more or less the first non-Russian, non-American modules to be attached to the International Space Station, and I had the chance to participate to this mission. To go there, we had the space shuttle, the U.S. space shuttle. It was mission 122, Space Shuttle Atlantis, and we carried inside the payload bay of the shuttle the Columbus module and a couple of other experiments. We're going to see that in a video that I will show you in 30 seconds. So that was a 2-week mission for the shuttle, but for me it was a little bit longer because I was flying there as a member of the International Space Station, so a crew member of the station. So the mission for me lasted a little bit longer, 2 months almost, 7 weeks exactly. And so I went up with Atlantis, Space Shuttle Atlantis, and went down with another space shuttle, which was Endeavour. And this was also an assembly mission of the station, which was bringing up the first module of the Japanese part of the station, which is a logistics module, and also a robotic hand that you might have seen in the station today. So it was also the delivery mission for this robotic hand. The robotic arm of the station was already in place for several years and was actively participating to the construction of the station. Okay, so I think we're going to start with the video, and hopefully we'll save time also for the questions, your questions afterwards. So you see Expedition 16, so that was the 16th crew of the station. Today we are starting Expedition 36, so it's going very quickly. At this time the duration of the mission was changing. I told you I flew during 2 months, but now the standard duration is about 5 or 6 months. So what you see here is the arrival of the Columbus module in Florida. So that was I think in June 2006, so more than a year before the launch. And you can see here an animation showing the let's say the architecture of the module, the structure of the module. This is a cylinder, relatively standard construction, with on one side hatch, of course, which is the part which is attaching to the station. On the other side, you see we have what we call an end cone, and with 2 external platforms. In these external platforms, we can put some external experiments. So here you see the interior of the module in this drawing. Very modular. We have racks for the systems, and we also have racks, of course, for the science, for the scientific facilities. So this is how it was installed in the shuttle. So in the aft part, the Columbus module, in the forward part, a platform with a couple of external experiments that we would have to install on the external platforms of the. So this is drawing from my son. I promised him that I would show it, and this was on February 7th. So we were leaving on the bus to join the launch pad. So we are already around 100 feet high in installing inside the shuttle. Unfortunately, I was installing in a mid-deck. So in a mid-deck, you don't have an external view of what is going on, which is a little bit too bad. So we have 4 people in the flight deck, which is the upper deck, with windows. So for them, of course, it's a blast. For those in the mid-deck, it's more based on sensations. But of course, you don't have external vision, unfortunately. So you sit more or less 2.5 hours on your back. So when you're launching, you're quite happy, I can tell you. And we were not sure at this time that we would launch because it looks like the weather is good, but it was not so good at that time. So 15 minutes before the launch, we were told that you see that there are some clouds here, and the shuttle, when it launches, should have a good weather because there is always a possibility that it would come back immediately, or not immediately, but in the next minutes to the launch site, and you want to, of course, to have a good weather to be able to return safely to the launch site. You might have seen a video from the external tank. So there is this one, like here. There is an external camera which is installed in the external tank to watch the launch. So it's not only to make good video, but that was a measure which was taken after the Columbia accident in 2003 to be able to monitor this tank. You might remember that the accident of Columbia was due to thermal insulation coming from the top of the external tank and damaging the leading edges of the shuttle wings. And so since then we are monitoring closely this we were, I should say, monitoring closely because the shuttle is not flying anymore since the last mission for the ISS a couple of years ago. So during 2 minutes, we are climbing with the external boosters, and more or less it's a vertical trajectory. So you're going out very quickly out of the atmosphere, and then you start to put your speed vector more or less in a horizontal direction to be able to accelerate to the orbital speed. So this is separation of the boosters after 2 minutes. At this time, the altitude about 200,000 feet. And the shuttle here is maneuvering, so it's pointing its back towards the sky to be able to establish contact with the satellite communication satellites. And we're already 8.5 minutes into the flight, and the separation from between the shuttle and the external tank. At this time, my colleague that you might have seen, Hans Schlegel, he was a German astronaut, another ESA astronaut on board. He crawled out of his seat and started to make pictures of this external tank. This was also a part of the safety measures which had been taken after the Columbia accident to make sure that there were no damage to the external tank, so he had to make pictures immediately. You have seen that we have opened the doors of the payload bay of the shuttle, and now we are starting this operation, which you might have seen that the first thing with the shuttle arm, the robotic arm, the basic robotic arm, we are taking an extension of the arm which is on the other side of the bay, and then you have a very long arm, and you're able to do this scanning of all the protections of the shuttle under the body. And during 2 days, you are drifting, we can say, to to be able to join the station. So this picture is taken from the station, and this is also one of these safety rules that we had established. The shuttle is doing maneuver, so you see it's flipping and showing its belly to the station, and at the same time you see on the right side in the animation the crew inside the space station is taking picture with 400 millimeters and 800 millimeters lenses of the protection tiles to be able to make sure that, again, that this has not been damaged during the launch. And then we are coming to the final phase before the docking. So the commander, who was Steve Frick, commander of the shuttle Atlantis, was manually flying the shuttle towards the docking. So it's all done manually. It was all done manually with the shuttle, so congratulations to him, of course. And here you can see we're already ingressing the station, and you can see Peggy Whitson, who was the commander of the station at this time. So she was my commander during 2 months on board the station. So I had a woman commander, and I would use the opportunity to say that yesterday we had the launch event for the women in aerospace in Paris, and that was actually Women in Aerospace Europe. And Fiorella is here, and she's the coordinator for those who don't know her. She's the coordinator for Women in Space Europe, and she will say a few words after this presentation, after your questions. It's always a great moment, of course, when you reach the station. Now you are not only 7 people in the shuttle station complex, but 10 people. At that time, there were only 3 people permanently living and working inside the station. Today, we have 6 permanently, almost, with, of course, exchange of the crews every, I would say, 4 months. So that's the beginning of this Atlantis mission. Unfortunately, we will not see the whole video, which is lasting about 30 minutes, so that would be too long for today. So we will just see the parts of the mission for the installation of the Columbus module. So we had a first, what we call EVA, or extravehicular activity. So 2 American astronauts went outside for this first EVA. And what they are going to do, and you can see it here, they are going to pick what we call a grapple fixture, which was attached to the wall of the shuttle in the payload bay, and attach it to the Columbus module. It looks like a simple thing to do, but it takes a few hours to do that, even with 2 people. And the purpose of this grapple fixture, as his name implies, is to be used by the robotic arm of the station to grapple the module and to attach it, and we will see that later, to the space station. You can see here one of the techniques which is very often used during the extravehicular activities. So the robotic arm, it might be from the shuttle or from the station. At the top you have a platform, and the astronaut is standing on the platform. He's attached, of course, and so he has his 2 hands free to be able to do all the things. And this is something which is used very often. At the end of this extravehicular activity, so the robotic work is starting, so we're extracting the module. There is an animation showing here how this was done. So of course it is much faster than the real operations, which usually takes 2.5 or 3 hours. So you see this is a complex cinematics, and we attach the Columbus module on the space station is here. See my cursor, maybe? So that's on the right side of the station. Maybe I will show you later why we call it the right side, but the station is going almost always in the same attitude, in the same, well, direction, I would say, on its orbit. And with regard to the speed vector, the Columbus module is usually attached to the right side, and forward and right side. So you see the final attachment here. So this was done by my colleague and friend, Leland Melvin. And at that time I was in this module, which is called the Node 2, which is the American module. And I was preparing to bolt the module. It's important to bolt it, of course, first before you equalize the pressures between the two modules. Because of course, if it's not well bolted, you can, when you equalize the pressure, you are depressing the whole thing. So it's not, would not be nice. So we want to make sure first that there is a good structural attachment of the module before you start equalizing the pressures with the rest of the station. You see here the two platforms I was talking about before, and we will attach during this mission a couple of experiments outside. One is called Solar, and it was an astrophysics or sun observation experiment, which is still working today after 5 years. And the other one was called UTEF, and it's more or less a platform with various experiments, including exposures of materials to the space environment. So here we are in the Node 2 module, which is the module where the Columbus is attached. Columbus is on the right here, so we are looking at it. And of course, that was a very nice moment for everybody. You know that people on the ground are working during a long time and years and decades for building things. And of course, it's a very important moment when we are reaching the final installation and starting to operate the module in space. And so my colleague Hans Schlegel is here. You know, you might see we're wearing goggles, and we had masks also. It happened in the past that on the ground before the launch, some modules were not cleaned up very well, I would say. And it happened that some metallic debris or metallic particles were floating in 0G, of course. And this is, of course, not nice for the crew, because you can breathe them, or they can go into your eyes. So you want to protect initially the crew from this kind of thing. But Columbus was very clean. We were happy. I think they had a good vacuum cleaner on the ground. You see here, maybe I will show you some pictures of what is Columbus today. You see here the first image of the, let's say, activation of the module. You see we are starting to open the rack panels, the storage rack panels, and here Yuri Malenchenko, who was my Russian colleague, is demonstrating a space dance. A very experienced space flyer, because I think he had more or less 4 long-duration flights in his career. So he's a very experienced guy. Peggy Whitson, that you can see here, she was a commander. I told you that was her second long-duration flight. So she spent during his first mission, I think, her first mission, 5 months, in space, 4 or 5 months, and this mission lasted 6 months more or less for her. We are here at the second extravehicular activity, which is not really dedicated to a Columbus, let's say, operations, but the objective was to, you can see here the airlock. And that was the first extravehicular activity for my colleague Hans Schlegel. Unfortunately, I was not scheduled to do this, to do an EVA, but I used the robotic arm instead, so which is also nice. And you can see here the face of Rex Walheim, which is a US astronaut, doing this second EVA with Hans Schlegel. So here we are in the payload bay of the shuttle, and you can see underneath there is a big box, which is the size more or less of a phone booth. The technique which is used here is still the arm carrying the astronaut, and the astronaut carrying a big box in his hands. The objective of this EVA was to replace a tank of nitrogen in the truss of the station. You can see that on the animation here. So the nitrogen tank, the old one, was extracted first by the crew, and then with the support of the robotic arm, we carried the new one, which is full of nitrogen, to replace it. And after that, the crew had to also fine-tune the external installation of the Columbus module by installing handrails, so the crews can move easily on the external surface of the module. And this is the third EVA. So there were third EVAs in this Atlantis mission. And at that time, I had the chance to use the robotic arm. So you see what we had to do. So we take one of these two experiments I was talking about before, and with this, again, arms cinematics, we are carrying it up to the upper platform of the Columbus module. We installed these two experiments, which was, as I told you, an astrophysics experiment and exposure experiment for materials study. During this EVA also, the crew had to bring back a failed piece of equipment of the station, something we call the control moment gyro, which is a big rotating ball, let's say, more or less, that we can use to change the attitude of the station. So without using the thrusters of the station itself, which are only on the Russian part. On the American part, you have these control moment gyros, and you have 4 of them, which can be used for reorienting the station without using the thrusters and without consuming propellants. So that was the last EVA. You can see here the change of light. We are, of course, flying around 7 kilometers per second or 28 kilometers per hour. So that means more or less every 30 minutes you see the sun going up or down. And this is the installation of one of our experiments. Very, very easy to do. You just put it on the platform. There is a magnetic piece of equipment which is stabilizing it, and then you just have to drill it with a tool that you might have seen before, and it's done. Here you can see the airlock. Looks big, but when you have 2 astronauts with their suits and you have all the tools and might have some big equipment, inside there is not much room left in this airlock, and it looks much smaller than it looks on the video here when you are inside. And the shuttle crew is still here, so we are using their manpower to start to activate as much as we can the Columbus module. Looking at the time, we don't have much time left for the questions. Yeah, thank you. But we are reaching the end here of this part of the video. So the shuttle will left the station, and I will stay for another 5 or 6 weeks on board. But this is another story. So I think we can stop here, and we can go to the questions. Thank you.
So if you have
always too long.
Perfect. So if you have questions, either you are right around the table and you can use these microphones, or I can pass this along. So are there questions? Please raise your hands.
Okay.
Okay. If I understand well, you've flown by Russian ways and American ones. By your astronaut point of view, can you explain and talk more about space flight with Soyuz and STS flights, STS missions?
What was the difference between the Soyuz and the shuttle?
Yeah, with the feelings of the takeoff and the re-entry.
Okay, yeah, I will try to say that in a few words, but it's very different, of course, because except for the launch, for me, I told you, in the mid-deck, so I didn't see anything outside. So when you go up, you just feel it. You have accelerations up to 3 Gs, more or less, but this is the same for the shuttle or the same for the in the Soyuz. And in the shuttle, of course, I told you already, those who are up in the upper deck, on the flight deck, they can see outside. And I was hearing the people screaming there. That was really fantastic. On the Soyuz, you don't have that, of course, and you are under a fairing when you're launching, so you just realize that you're in space when the fairing is gone, and you're able to watch outside, which is very interesting because you launch, from a Soyuz launch, it was dark, cold, and then all of a sudden you are flying over the Pacific, and it's blue and looks like I would say summer environment. For the return, it's very different. The Soyuz, as you know, is a capsule, so when you go back, you have to maybe up to 4 or 5 Gs, and then you open the parachute, and the capsule is moving in all directions, so that you're a little bit disoriented. In the shuttle, nothing like that. I would say it's even smoother. For me, I had that feeling smoother than flying in some airliners. I didn't even feel the wheels touching the runway when I came back in March 2008. And on the Soyuz, of course, when you hit the ground, it is also a different story. You have rockets igniting about a meter height, and of course it slows you down, but not so much. Other questions?
Yeah. I have a question. Now it should be on. Yeah. How is the feeling when you outside in the spacesuit? I mean, when you inside the shuttle or inside the station, it's still one atmosphere. You are weightless. But when you go outside, it's lower pressure. You have the suit which limits your move. So how is the feeling? And
so you didn't listen very well, because I I say that I didn't go outside, unfortunately, but I have trained for that, of course. And what I can tell from the suit, at least, because I use it in the pool, that's something which is very hard to use, because it's inflated. Of course, you have about 0.5, 0.4 atmosphere inside, so it's about half the pressure on the Earth, on the ground. But it's very hard to move, and especially for the fingers. So when you have 6 or 7 hours in this suit, it's very tiring.
And maybe a second half of the question is it true that you use a special medication or some when you go outside just so people can perform the job properly, or?
No medication, and this is part of the safety rules. We have no medication, but you have some, like when for the divers when you're going water diving, it's you have to respect certain rules for before you go outside, and especially to breathe some oxygen, pure oxygen, during a certain time, to be able to get rid of the nitrogen which is in your body, just like the divers. But no medication, because I don't think this is appropriate for someone who is going outside. Just like for pilots, it's the same thing. Other questions?
When on both launchers, yesterday we were talking with CNES people about the destruction function. So when there are flying, when there are humans inside, is there a kind of ejection module on top, or is it part of the risk? How does it work?
So in the very first flights of the shuttle, they had some ejection seats, but you only had 2 people on board. I think that was for the first 2 or 3 missions. I don't remember exactly. But they had 2 ejection seats. But of course, ejection seats, you can use them just in a small part of the flight domain of the shuttle, of course. You can use them when you have very low speed and you're still in the atmosphere, more or less. On the Soyuz, you have an ejection system, but this is for the whole capsule. So this is true. This was true also, I think, for the Apollo mission. If you look at the Apollo launchers, you see on top of the capsule, you can see an ejection tower, which is there for ejecting the capsule only in case you have launcher failure on the ground or even later during the launch. So this is for capsule. This is easy to do. For the shuttle, it was much more complex, because the shuttle itself was the ejection seat, I would say. If you have a problem during the launch, you have several phases in the launch where you can return to the launch site, or you can go also transatlantic only, so you don't reach the orbit, but you reach a landing site or an airfield in Europe. So I would think at that time that probably the fastest way to bring the Columbus module back to Europe, but that was not the objective. And you can also, with the shuttle, you had also the possibility to abort, they say, after 1 orbit. So you go back and land in Florida or elsewhere on the trajectory. Other questions?
Actually, it was the 5th anniversary of the Columbus module installation. What is the most amazing result, you know, that came through with Columbus?
It will take a long time to, of course, to talk about the all this research that we are doing. But what I can say is that we have on board Columbus several racks which are dedicated, several facilities which are dedicated to research, space research. We have some also experiments outside, as I said before. So more or less we have 4 racks which are European racks dedicated to science research, but we also, let's say, rent or we bartered some racks or some part of the Columbus volume to the Americans. So they are also using it for research. So we have a human research facilities, for instance, inside. We have a biological research facility that I used from the beginning. So that was the first experiments that we did in Columbus, and the objective was to grow a plant in 0G and see how the growing process was going. That's always interesting because you know that gravity is very much involved. We think in the growth of plants, but it's always interesting to see how it goes when you are in 0G, so without gravity. But we also have a physiology facility. So we're making a lot of research of course we have astronauts on board, so it's very interesting for the researchers because you have subjects on board, and the astronauts are also subjects of research on board, even if we are not doing anything invasive, of course, because you know that we don't want to risk anything. We don't have a hospital on board. We have a small hospital, but we don't have surgery, we don't have anything, so we will not try to do anything which is, of course, could threaten the life of the astronauts. But in general, in the ISS, you have maybe 100 research facilities that you can reconfigure. And this is, of course, something which is unique and that we didn't have before. So again, I don't want to spend too much time on the answers. Maybe, I don't know how we were doing on time.
And maybe just a word from...
Yeah, I mentioned during the video that my commander was Peggy Whitson, so she was a woman, experienced, talented, and I would like to give the word to Fiorella, who's going to talk to you about maybe 1 minute or 2 about women in aerospace Europe, or overall in the world.
I'm Fiorella Coliolo. I'm an astrophysicist by training, and I work in communication with ESA mainly. And yesterday we just launched the Paris group of Women in Aerospace Europe. I see a lot of women around this table. It's also open to men. It's an European organization. The objective is to expand women opportunities for leadership in aerospace. So if you like to join the association, I can give you more information after the presentation. And I'm responsible for the local group in Paris, but we have different local groups in Germany, in Netherlands, in Belgium. And when you join the association, you join Women Aerospace Europe, not a different local group. So if you are interested, please come to see me after the presentation.
So thank you a lot to Leo and Fiorella, and I think we can applaud.
Thank you.
So now we are going to have a short break. And after this break, so we plan to have at 4:15 the next section. That's in a very short time. So we're going to do it at 4:20 for the next session. But then we'll shorten it by 2 minutes to keep with the overall schedule. So now, please go to the main hall where you're going to have a small pause, and then at 4:20 in the various rooms.